So I said in the last two classes or three, we've been on data visualization using Python. And our main purpose of doing this is to help us with data exploration as we move on with the data analytics course. Okay, so we saw how to plot scatter plots, line plots, pie charts, bar charts, okay, histogram, and so on. Okay, in the class before this, we saw histogram and all that. And we also saw how to include our legends, how to include titles, Y ticks, X ticks, and so forth. Okay. We also saw how to do multiple plots and subplots. Okay. We saw that in the last class. So today, what we are going to do is to take a look at some very important analytics concepts that will prove useful as we go on with the course. Okay. General analytics concepts now that will help us, some things that we need to know generally, that would serve as foundation for our analytics, for our data analytics. So, specifically, we are going to be looking at some of these topics. In particular, we are going to be looking at the normal distribution. Okay. Yeah, I think data types, we dealt with data types before. I think we've also done measures of position. Okay, but we are paying special attention to normal distribution. Okay. In fact, generally, we are doing a review of all these topics, but with special attention to the normal distribution. Okay. Which is very, very important as far as data analytics is concerned. All right. Then for topics that we already are used to, we are not going to waste time on such, on such. Okay. Standard data type. Generally speaking, data may be classified as categorical and numeric. Under categorical, we have the nominal data, we have the ordinal data. Numerical, we have discrete, continuous. Continuous data, we have interval ratio. Okay. Is this clear the way we know all this, right? Can we proceed? Do we remember this? Remember them?
Yes, sir.
Okay. So let's proceed. Don't need to waste time on it. Measures of position. A measure of position determines the position of a single value in relation to other values in a sample or a population data set. Like the mean and standard deviation, descriptive measures based on quantiles are not sensitive to the influence of few extreme observations. Okay. So measures of position, or talk of measures of position, we are talking essentially about quantiles, basically. Okay. Especially the most commonly used measures of position are percentile, quartiles, and standard scores, also called z-scores. Okay. You know, in descriptive statistics, we talk about things like measures of central tendency, measures of dispersion like mean, median mode, variance, standard deviation. Then there's also measures of position. That's where we have percentiles, quartiles, and so forth. Okay. The other time we're looking at the um, when we're looking at the plots, when we're looking at the plots, we saw 1 minute. Yeah, so when we're considering the various plots charts, we saw the box plots. Okay. And the box plots, I told you, is used for what is called the 5-number summary. What are the 5 numbers we are talking about? Can someone remind us what are these 5 numbers? Are we still there?
The 5 numbers of what, sir?
In a box plot, we call box plot a 5-number summary.
Okay.
Do you remember that?
We have the first quartile,
Yes.
the second, the median,
Yes.
the, the second quartile, then the
Yes. Hello.
yes, the other was of escapes my head.
Okay. Okay. We have the minimum. We have the first quartile, the median, which is second quartile, the third quartile, and the maximum. Okay. You
Yes.
see, what I'm asking you, see, that one is based on measures of position. Okay. That's plots based on measure of position. And that plot, that box plot is a very, very important kind of plot used for observing the shape of data, used for data exploration. Okay. And yet it makes use of measures of position. That's to just, I'm saying all this to underscore the fact that measures of positions, most position are very important as well. Okay. All right. So percentile is based on percentages. Quartiles, we have first quartile, second quartile, which is median, third quartile. You know, first quartile is like one quarter position. Second quartile is half, middle. Third quartile is 3/4. Okay. Then we also have the standard scores, the z-scores. Okay. Yeah. So we have the z-scores. Z-scores is based on the standard normal distribution. As we are going on, if you have any question, please don't hesitate to ask, because this is just a brush through. We're not going to waste much time here. To lay the foundation for us to continue with analysis. Okay. But from next class, we are going to, start handling the real analysis as we, advance towards the end of the course. So we need to lay foundation. Okay. I know we know these things, but just a brush up. This is more or less revision now. Okay. All right. Now the normal distribution. Normal distribution, also known as the Gaussian distribution, is a probability distribution that is symmetric about the mean, showing that data near the mean are more frequent in occurrence than data far from the mean. Okay. And we know it's a bell-shaped distribution. Okay. In graphical form, the normal distribution appears as a bell-shaped curve. And it's very important to know that when you look at the normal distribution, this distribution this diagram you are seeing now, this is not just the normal distribution. This is like standard normal distribution. Okay. Now you can see at the middle we have sorry, no, this is normal distribution. It's normal distribution. So at the middle here we have the mean, and the normal distribution, the mean of the distribution corresponds with the median and the mode. Okay. Then as you move toward the right, you see that between this point and this point, we have one standard deviation, two standard deviation, three standard deviation. Okay. And you see that the data between the values between minus one standard deviation and plus one standard deviation represent 68.2% of the entire population of data. Okay. So that tells you that most of the data are concentrated around the center. Why? Because we can see that the center is high and then it's, has a peak, right? Then between minus two standard deviation and two standard deviation, we have 95.4%. Okay, so we just left with a few. So the values at the extreme are very, very few. Okay, so that's the nature of standard deviation. Now, the normal distribution, the key points to note is that the normal distribution is the proper term for a distribution, a probability bell curve. The normal distribution, the mean is 0 and standard deviation is 1. In a normal distribution, the mean is 0. So actually, that's what we are describing as the standard normal distribution. In a standard normal distribution, the mean is 0 and the standard deviation is 1. It has 0 skew and a kurtosis of 3. Normal distributions are symmetrical, but not all symmetrical distributions are normal. So that's very, very important. That to note that a distribution is symmetrical does not mean that it is normal. Okay. A distribution can be symmetrical, yet the kurtosis may not be 3. So that would not be a standard normal distribution.
When you say symmetrical, what do you mean?
Yeah, what we mean is, if you look at this, if you cut this figure into 2 parts, you see that the left side and the right side will be exactly the same thing.
Yes.
That's what we mean by being symmetrical.
They must have two equal halves.
Yes. So the right and the left, they are like mirror image of each other.
Okay.
That's a symmetrical distribution. Okay. Yeah. So normal distributions are symmetrical, but not all symmetrical distributions are normal distributions. So a distribution may be symmetrical and yet not normal. Many naturally occurring phenomena tend to approximate the normal distribution. Okay. Can we give an example of a natural phenomenon that approximate the normal distribution? Can somebody give us an example of that? Oh, okay, okay. Go ahead, please.
Is it -0 to +1, then +1, and so forth from the negative side to the positive side?
What I'm saying is, can you give example of some measures in nature, some things naturally that follow or approximately that are approximately normal. You know, some values that when you measure them, they tend to take this shape. Can you think of anything like that? You know, when we're talking of distributions, it's not just a random thing. These are measurement of, certain data values, okay? Data sets that have been taken, various data sets. So those data sets, when you measure the values, in some cases, they conform to normal or approximate the normal distribution. So can you cite any example of such data sets or such measurements or values? Okay, let me give you an example. For example, the scores of students in JAMB, in an exam like JAMB. That's an example. Another example,
Okay, now
the
can you
high, what?
percentage?
Percentage. Hello?
Like we can use percentage.
No, what I'm saying is this. You see, an exam like JAMB, for example, right? If you take the scores of students, all the students that write JAMB, all the students that write JAMB, you take their scores, you measure their scores, and you plot it, okay? Maybe using something like a histogram. You do a histogram. If you want to use histogram um, to chart the scores of the students, how would you do that? What will be the x-axis? The x-axis will be the scores, okay? from 0 to whatever, maybe 0 to, is it 400? And then the y-axis will be the frequency, the number of people that got each score. Okay. If you do that, you discover that the mean score, around the mean score, okay, you find that out that most of the people will cluster around the mean score. If it's over 400, or okay, if we are using percentage, that will be 0 to 100. Let's say the mean score is 45, for example. You see that most of the people, a good number, very large number of persons, will have scores around that. Okay? Then the extremely low scores will be few. Extremely high scores will be few. So that's an example of a natural phenomenon that approximates the normal distribution. Is it clear? Understood? Is it understood? Any question?
Can you just come again, sir? Just sorry.
Okay.